On the 5th of September, 1977, a rocket lifted off from Cape Canaveral, Florida, carrying a spacecraft the size of a small car and weighing 722 kilograms. The launch was not the most powerful in NASA's history. The spacecraft was not the largest ever built. The mission did not carry astronauts and was not aimed at the Moon or Mars or any destination that would register as meaningful to most people following the news that day. It was aimed at the outer solar system, at the giant planets, at a trajectory that would carry it past Jupiter and Saturn and eventually out of the planetary neighborhood entirely on a one-way journey with no planned return, no destination, and no end date. 46 years later, that spacecraft is still flying. Voyager 1 is currently more than 23 billion kilometers from Earth. The signal it transmits, a radio wave traveling at the speed of light, takes more than 22 hours to reach the receivers at NASA's Deep Space Network. The engineers who receive that signal, who decode it and analyze it and use it to understand what Voyager is experiencing in the environment it now occupies, were not born when the spacecraft was launched. Some of their parents were not born when the spacecraft was launched. The scientists who designed the mission, who calculated the trajectories and selected the instruments and made the thousands of engineering decisions that allowed a 722-kilogram machine to survive and function for nearly 5 decades in the most hostile environment imaginable, are mostly gone. The spacecraft they built is still out there, still moving, still transmitting, still the farthest object humanity has ever placed in the universe. No other human-made object has traveled as far. No other mission in the history of spaceflight has covered more distance. Voyager 1 holds the record for the most remote human artifact in existence by an enormous margin, and it will hold that record for the foreseeable future. There is no mission currently planned, no spacecraft currently in development, no technology currently available that will send an object farther from Earth in the next several decades than Voyager 1 has already gone. By any measure of distance covered, it is the greatest achievement of human engineering in the history of the species. And yet, Voyager 1 has not left the solar system. This statement requires a pause because it contradicts something that many people believe they already know. You may have read a headline, perhaps a decade ago, announcing that Voyager 1 had crossed into interstellar space. That headline was accurate in a specific technical sense, referring to a boundary called the heliopause, where the solar wind, the stream of charged particles continuously emitted by the sun, finally loses enough pressure that the interstellar medium takes over. Voyager 1 crossed that boundary in 2012. In that sense, yes, it entered interstellar space. But interstellar space is not the edge of the solar system. The solar system does not end at the heliopause. It extends far, far beyond into a region so vast and so poorly understood that its outer boundary is not a line on a map, but a gradual fading of the sun's gravitational influence into the gravitational background of the galaxy. The solar system, defined by where the sun's gravity still holds sway over orbiting objects, extends to something called the Oort Cloud, a vast spherical shell of icy bodies that surrounds the sun at distances ranging from roughly 2,000 to 100,000 times the distance between Earth and the sun. Voyager 1 is currently at approximately 160 times that distance. To reach the inner edge of the Oort Cloud, it would need to travel more than 10 times farther than it has already gone. To exit the Oort Cloud and truly leave the solar system behind, it would need to travel hundreds of times farther still. At its current speed, Voyager 1 will not exit the Oort Cloud for approximately 30,000 years. That number deserves to be repeated. 30,000 years. The agricultural revolution, the event that allowed human civilization to begin in any recognizable form, occurred approximately 10,000 years ago. Writing was invented around 5,000 years ago. The entirety of recorded human history fits within the last 5,000 to 6,000 years. The spacecraft we launched in 1977, the farthest and fastest object humanity has ever placed in space, moving continuously at a speed that would carry it from Earth to the Moon in under 4 hours, will not exit the solar system for 3 times the entire span of recorded human history. The solar system is not large in the way that a continent is large, or the way the Earth is large, or even the way the distance to the Moon is large. It is large in a way that defeats comparison to anything within ordinary human experience. Every scale model, every diagram, Every attempt to represent the solar system's true dimensions on a page or a screen necessarily distorts the distances so severely that the resulting picture is more misleading than informative. The planets are shown with gaps between them that suggest a navigable neighborhood, when in reality the distances are so enormous that the planets themselves, despite being thousands of kilometers across, would be invisible to the naked eye from the distances that separate them. The story of how Voyager 1 achieved its extraordinary velocity, how a 722-kilogram machine launched in 1977 reached speeds that no rocket technology of the era could have directly produced, is a story about one of the most elegant pieces of physics ever exploited by human engineers. It is the story of the Grand Tour, a mission concept that had been proposed for years before anyone confirmed it was actually possible, and that depended on a celestial alignment so rare that the window for executing it would not open again for 175 years. Every 175 years, the four giant outer planets of the solar system, Jupiter, Saturn, Uranus, and Neptune, align on the same side of the Sun in a configuration that allows a spacecraft to visit all four in a single continuous trajectory, using the gravity of each planet to accelerate toward the next. The mechanism is called a gravitational assist, or slingshot maneuver, and it exploits the same physics that governs the interaction between any two massive objects in motion. When a spacecraft passes behind a planet relative to the planet's direction of orbital motion, the planet's gravity pulls the spacecraft forward and slightly inward, then releases it with greater velocity than it had before the encounter. The planet loses a tiny, unmeasurably small amount of orbital energy in the transaction. The spacecraft gains a significant fraction of the planet's orbital velocity. No fuel is consumed. The energy comes from the planet's motion around the Sun, borrowed for a moment, and transferred to the spacecraft through the geometry of the encounter. Voyager 1 performed this maneuver at Jupiter in 1979, arriving at a velocity of approximately 10 kilometers per second and departing at more than 17 kilometers per second after the Jovian slingshot. It was the gravitational energy of the largest planet in the solar system, accumulated over the 4.5 billion years of Jupiter's orbit, that gave Voyager its extraordinary speed. The spacecraft's rockets, the actual propulsion system it carried, were used primarily for trajectory corrections and orientation adjustments. The velocity that carries Voyager 1 through interstellar space today was given to it for free by Jupiter. 17 kilometers per second, 61,200 kilometers per hour, more than 50 times the speed of a rifle bullet, more than enough to escape Earth's gravitational field, more than enough to escape the Sun's gravitational field, which is why Voyager 1 is on a hyperbolic trajectory that will never bring it back. It is moving fast enough that gravity will never reclaim it. It will travel outward forever, or until some other gravitational influence, some star it passes near in millions of years, captures it or deflects it. 17 kilometers per second sounds, and by human standards genuinely is, an extraordinary speed. It is faster than anything most people will ever directly experience by a factor of several thousand, and it is, in the context of the distances it needs to cover, to reach even the nearest star, essentially stationary. The nearest star system to our own, the triple star system Alpha Centauri, including Proxima Centauri, is approximately 4.24 light-years away. A light-year is the distance light travels in 1 year, moving at 299,792 kilometers per second. At Voyager's speed of 17 kilometers per second, covering that distance would require approximately 73,000 years. 73,000 years to reach the nearest star, traveling continuously at a speed that feels, from any human perspective, almost incomprehensibly fast. This is the number that changes everything. Not because it means interstellar travel is impossible, not because it proves that humanity will never reach another star, but because it establishes the actual scale of the problem with a clarity that no amount of abstract description can match. The solar system is not a neighborhood within a larger neighborhood. It is an island. The distances between stars are not large in the way that the distance between cities is large, a matter of hours or days of travel. They are large in a way that makes even the concept of travel across them with any technology we currently possess, or any technology we can currently envision building. An exercise in timescales that exceed civilization itself. And Voyager 1, the farthest and fastest thing we ever threw, is the proof. It is moving at the maximum speed our engineering could achieve, using the gravitational energy of the largest planet in the solar system as a free boost. It has been flying for longer than most people alive today have been alive. It has covered a distance so large that its radio signal takes nearly a full day to reach us at the speed of light. And it is still, by the standards of the universe, in our backyard. Still inside the solar system. Still decades away from even the preliminary boundary of the space between stars. Still nowhere near the destination that a child looks up at on a clear night and calls the night sky. The question of how far our best spacecraft can actually go, and what stands between here and there, is not a question with an encouraging answer in the short term, but it is a question with a remarkable answer. An answer that, when you follow it all the way down through the physics and the engineering and the mathematics of distance and time, arrives somewhere that is simultaneously humbling and extraordinary, somewhere that changes what the night sky looks like when you step outside and look up. That is where nocturnal space is going tonight. Through every layer of the problem. The speed limits that physics imposes. The true boundaries of the solar system. The technologies being built and imagined to push past what Voyager achieved. The paradox of a universe that appears to be full of stars and almost certainly harbors other worlds. But that is structured in a way that makes reaching any of them almost impossibly difficult. And at the end, the honest answer to what all of this means for a species that has been looking up at those stars for as long as it has been capable of wonder. Subscribe to Nocturnal Space if you have not. Turn on notifications. This is the kind of story that starts with a spacecraft and ends somewhere you did not expect to be when you pressed play. And we are only just beginning. Voyager is still out there, still moving, still transmitting. And the universe it is moving through is stranger and larger and more indifferent to our ambitions than anything the engineers who built it could have imagined when they watched it climb away from Cape Canaveral on that September morning in 1977. We are going to follow it all the way to where the answer lives, There is a number that appears in almost every discussion of Voyager 1's journey that sounds, on first encounter, like it should be enough. 17 kilometers per second. It is the number that gets cited in news articles and documentary narrations and science communication videos as evidence of the extraordinary achievement that Voyager represents. 17 kilometers per second. And the number is genuinely extraordinary by every standard available to human experience. It is fast enough to travel from New York to Los Angeles in under 4 minutes, fast enough to circle the Earth at the equator in under 40 minutes, fast enough to travel from Earth to the Moon in less than 4 hours, fast enough to escape the gravitational pull of the Sun entirely, which is why Voyager 1 is on a trajectory that will never bring it home. By any measure derived from human experience, 17 kilometers per second is not just fast, it is incomprehensibly, almost offensively fast. It is faster than a bullet by a factor of 15, faster than the speed of sound by a factor of 50, faster than a commercial aircraft by a factor of nearly 600. If you were somehow able to perceive the passage of time at the scale where 17 kilometers per second felt like a normal walking pace, the entire history of human civilization would pass in a fraction of a second. And it is nowhere near fast enough, not almost fast enough, not fast enough with some modest improvements in propulsion technology, not fast enough in a way that better engineering could fix within a few decades of research and development. Nowhere near fast enough in a way that reveals something fundamental and uncomfortable about the relationship between the scale of the universe and the physical constraints on motion within it. Understanding why requires understanding something about how rockets actually work, something that most people who think they understand rockets do not fully appreciate, because the reality of rocket propulsion is significantly more brutal than the popular picture suggests. The physics of rocket propulsion is governed by an equation derived in 1903 by a Russian schoolteacher named Konstantin Tsiolkovsky, who spent his career in a small town outside Moscow working out the mathematics of space travel decades before anyone took the idea seriously. Tsiolkovsky's rocket equation relates 4 quantities: the final velocity a rocket can achieve, the exhaust velocity of the propellant being expelled, the initial mass of the rocket including its fuel, and the final mass of the rocket after the fuel has been consumed. The relationship between these quantities is not linear, it is exponential, and the exponential nature of the relationship is what makes rocket propulsion so brutally inefficient as a means of achieving very high velocities. The equation says, in essence, that to increase your final velocity, you need to increase the ratio of your initial mass to your final mass. If you want to go twice as fast, you need the exponential of twice the velocity to exhaust velocity ratio, which means you need dramatically more fuel relative to your payload, not twice as much, but many times more. To go 10 times as fast, you need an absurd, practically unrealizable mass ratio. The fuel required grows so rapidly with desired velocity that there is a practical ceiling beyond which chemical rocket propulsion simply cannot go, regardless of how efficiently you engineer the combustion, regardless of how light you make the spacecraft, regardless of how cleverly you design the nozzle geometry. Voyager 1 reached its extraordinary speed, not primarily through rocket propulsion, but through gravitational assists, borrowing energy from the planets it flew past. The actual rocket burns that Voyager performed during its journey were relatively modest by the standards of what would have been required to achieve the same final velocity through propulsion alone. If NASA had tried to send Voyager directly to its current position using only rocket thrust, the amount of fuel required would have been so large that the launch vehicle needed to carry it would have been physically impossible to build with 1970s technology, and arguably impossible to build with any technology that has existed since. The gravitational assist was not a clever trick that made the mission slightly more efficient. It was the mission. Without Jupiter, Voyager does not exist in its current form. But the gravitational assist has a fundamental limitation that constrains its usefulness for reaching other stars. The energy you can extract from a gravitational slingshot is limited by the orbital velocity of the planet you are using. Jupiter orbits the Sun at approximately 13 kilometers per second. You cannot extract more energy from a Jupiter slingshot than Jupiter's orbital energy can provide, and in practice you extract significantly less. Voyager's current speed of 17 kilometers per second represents roughly the practical upper limit of what gravitational assists from the available planets can achieve. To go significantly faster than this using the same technique would require either a planet moving faster than Jupiter, which none of the accessible planets does, or a flyby of the Sun at extremely close range, which is what the Parker Solar Probe achieves. The Parker Solar Probe is currently the fastest human-made object ever recorded in terms of speed relative to the Sun, having achieved velocities exceeding 190 kilometers per second during its closest solar approaches. This sounds dramatically faster than Voyager, and in one sense it is, but the Parker Solar Probe is not escaping the solar system. It is in a highly elliptical orbit that brings it repeatedly close to the Sun, accelerating to its maximum speed at closest approach, and then slowing as it swings back out. Its maximum speed is achieved because it is falling toward the Sun, not flying away from it. The enormous kinetic energy it accumulates on the inward leg is given back to the Sun's gravitational field on the outward leg. If Parker Solar Probe were somehow redirected onto an escape trajectory at its maximum speed, the numbers would change dramatically. But redirecting it requires exactly the kind of propulsive energy that the rocket equation makes so punishing to achieve. New Horizons, the mission to Pluto launched in 2006, was the fastest spacecraft ever launched directly from Earth, achieving a speed of approximately 16.26 kilometers per second relative to the Sun at launch through a combination of rocket propulsion and a gravitational assist from Jupiter. It is currently moving at roughly 14 kilometers per second, slightly slower than Voyager because it did not benefit from Saturn's additional slingshot. At its current speed, New Horizons would take approximately 78,000 years to reach Proxima Centauri if aimed in that direction. The difference between 73,000 and 78,000 years is not the kind of difference that changes the fundamental nature of the problem. The Helios probes, launched by a joint NASA and West German program in the 1970s, achieved speeds of approximately 70 kilometers per second during their closest solar approaches, making them the fastest objects ever built by humans in terms of instantaneous velocity relative to the Sun at the time of their measurement. But again, This speed was achieved by falling toward the sun from a significant distance, not by accelerating away from it. The energy came from the sun's gravitational field, and returning to the sun's gravitational field would cost every kilometer per second gained. Helios was not a precursor to interstellar travel. It was a very fast solar probe. The brutal arithmetic of the rocket equation has been understood since Tsiolkovsky derived it, and the response of the engineering community has been, essentially, to work within its constraints rather than to challenge them. Every rocket ever built, from the earliest liquid-fueled experiments of the 1920s and 1930s to the most powerful launch vehicles operating today, obeys Tsiolkovsky's equation without exception. The advances in rocket technology over the past century have been real and significant, involving better propellants, better engine designs, better materials, better manufacturing, staging systems that discard empty tankage to reduce the mass being accelerated. But none of these advances have changed the fundamental relationship between desired velocity, exhaust velocity, and mass ratio. They have optimized within the constraints. They have not escaped them. The exhaust velocity of the best chemical rocket propellants currently available, liquid hydrogen and liquid oxygen burning in a highly efficient engine, is approximately 4.4 kilometers per second. This is the fundamental limit imposed by the chemistry of combustion, the speed at which the reaction products leave the nozzle, and it determines the ceiling on what chemical rockets can achieve. No matter how clever the engineering, no chemical rocket can produce an exhaust velocity significantly above this number because the energy available in chemical bonds is finite and well characterized. To reach significantly higher exhaust velocities, you need a different energy source entirely. Nuclear reactions release roughly 1,000,000 times more energy per unit mass than chemical reactions. Antimatter annihilation releases energy at the theoretical maximum determined by Einstein's mass-energy equivalence. These are the directions that serious proposals for interstellar propulsion have explored, and they will occupy a later part of this story. But before going there, before discussing what might be possible in principle with technologies that do not yet exist, it is worth being precise about what the current situation actually is. The fastest spacecraft ever launched is moving at 17 kilometers per second. The fastest speed ever achieved by a human-made object during normal operational flight is approximately 70 kilometers per second. The speed of light is 299,792 kilometers per second. The nearest star is 4.24 light-years away. At 70 kilometers per second, reaching Proxima Centauri would take approximately 18,000 years. At the speed of light itself, it would take 4.24 years. The gap between what we have achieved and what physics ultimately permits is a factor of roughly 4,000. The gap between what we have achieved and what would make interstellar travel practical on human timescales is a factor of at least several hundred, possibly more. These numbers do not represent a temporary engineering shortfall. They represent the current position of humanity on a curve of technological development that has been progressing for only a few centuries, and that confronts a physical challenge of a scale that no previous technology in human history has had to address. Understanding how large that challenge actually is requires understanding something that most people, even people who follow space science closely, significantly underestimate. It requires understanding where the solar system actually ends, what lies between its boundary and the nearest star, and why the picture of the solar system that most people carry in their heads from school diagrams and documentary graphics is not just simplified, but fundamentally, deeply wrong about the scale of what surrounds us. The boundary of the solar system is not Neptune. It is not even close to Neptune. And the distance between Neptune and the actual edge of the solar system is itself larger than most people's intuitive sense of the distance from the Sun to Neptune. The solar system is so much larger than the region of planets, so much larger than the orbits that spacecraft have actually visited, that the entire history of human space exploration to date represents a journey across the front yard of a property whose back fence is thousands of times farther away. That property, its actual dimensions, the physics of what lies within it. And why Voyager 1, after 46 years of continuous flight at 17 kilometers per second, is still deep inside it and will remain so for thousands of years to come. That is where we are going next. Ask most people where the solar system ends, and they will tell you Neptune, the 8th planet, the last of the 4 gas giants, the blue world at the outer edge of the planetary neighborhood, orbiting the Sun at a distance of roughly 4.5 billion kilometers, so far from the warmth and light of the Sun that a year on Neptune lasts 165 Earth years, and the temperature at its cloud tops hovers around -200 degrees Celsius. Neptune is where the planets end. It is where the diagrams in every school textbook end. It is where the mental map that most people carry of the solar system ends, with a small label saying outer solar system and then an implied boundary beyond which nothing of significance exists until you reach another star. This picture is wrong by a factor of roughly 20,000, not 20%, not twice, 20,000 times. The actual outer boundary of the solar system, the region where the Sun's gravitational influence finally yields to the gravitational background of the galaxy, is approximately 20,000 times farther from the Sun than Neptune. The distance from the Sun to Neptune is not a useful unit for thinking about the solar system's true extent. It is a useful unit for thinking about the planetary neighborhood, the small, well-mapped, relatively well-understood inner region that spacecraft have actually visited. But the solar system extends vastly, almost incomprehensibly, beyond that neighborhood into a region that no spacecraft has ever reached, that no telescope has ever directly observed, and whose existence is inferred primarily from the behavior of comets that occasionally fall inward toward the Sun from its outer reaches. To understand the solar system's true structure, it helps to build it up layer by layer, starting from what is familiar and moving outward into what is not. The planetary region extends from Mercury at roughly 0.4 astronomical units from the Sun to Neptune at 30 astronomical units, where 1 astronomical unit is defined as the average distance between Earth and the Sun, approximately 150 million kilometers. This is the region of the solar system that spacecraft have explored, that planetary scientists have studied in detail, that appears in textbooks and documentaries, and the mental maps of anyone who has paid attention to space science. It is a disk of roughly 30 astronomical units radius, containing the 8 planets, their moons, and various smaller bodies. Voyager 1 passed the orbit of Neptune in 1989, 12 years after launch. It was, in terms of the actual solar system, just getting started. Beyond Neptune lies the Kuiper Belt, a region of rocky and icy bodies extending from roughly 30 to 50 astronomical units from the Sun. Pluto lives here, along with thousands of other objects of similar or smaller size, the remnants of the outer solar system's formation that never accreted into a full planet under the gravitational influence of Neptune. The Kuiper Belt is in some ways an extension of the asteroid belt, but colder, more distant, and populated by icier bodies that formed in the outer solar system where temperatures were low enough for volatile compounds like water, methane, and ammonia to freeze. New Horizons flew through the Kuiper Belt on its way to its Pluto encounter in 2015 and its subsequent flyby of the Kuiper Belt object Arrokoth in 2019. The outer edge of the Kuiper Belt, at roughly 50 astronomical units, is where our direct observational knowledge of individual solar system objects begins to thin dramatically. Beyond the Kuiper Belt, extending from roughly 50 to perhaps 1,000 astronomical units, is a region called the scattered disk, a sparse population of objects with highly elliptical orbits that were gravitationally scattered outward by Neptune during the early solar system. Some of these objects have orbits so elongated that their closest approach to the Sun brings them into the inner solar system, while their farthest point carries them thousands of astronomical units out. Sedna, discovered in 2003, has an orbit that carries it between roughly 76 and 937 astronomical units from the Sun, with an orbital period of approximately 11,400 years. It is one of the most distant known objects in the solar system with a confirmed orbit, and its existence hints at structures in the outer solar system that we are only beginning to understand. Voyager 1 crossed 100 astronomical units in 2006, 29 years after launch. At that distance, it was still well within the heliosphere, the region of space dominated by the solar wind. the continuous stream of charged particles emitted by the sun. The boundary of the heliosphere, called the heliopause, is where the solar wind's pressure finally drops to the point where it is balanced by the pressure of the interstellar medium, the thin gas and magnetic field that fills the space between stars. Voyager 1 crossed this boundary, as mentioned, in 2012 at a distance of approximately 121 astronomical units. This is the boundary that the 2012 headlines were referring to when they declared Voyager had entered interstellar space. But here is where the definition of the solar system becomes critically important. The heliopause is the boundary of the heliosphere, the region filled by the sun's particle wind. It is not the boundary of the sun's gravitational influence. Gravity is a long-range force. It weakens with distance, but never reaches exactly zero. The sun's gravitational influence extends far beyond the heliopause, far beyond the scattered disk, far beyond any region that any spacecraft has ever visited or will visit within any planning horizon currently imaginable. This is where nocturnal space needs to pause for a moment, because what comes next is one of those pieces of scientific information that sounds straightforward when stated, but requires time to actually absorb. The sun's gravitational influence, the region within which objects are gravitationally bound to the sun and orbit it rather than drifting freely through the galaxy, extends to something called the Oort Cloud. And the Oort Cloud is not a modest extension beyond the heliopause. It is a structure so vast that describing it in the same units used for the planetary region produces numbers that feel like errors. The Oort Cloud is a spherical shell of icy bodies surrounding the sun at distances ranging from approximately 2,000 to 100,000 astronomical units, 2,000 to 100,000. The outer edge of the Oort Cloud is roughly 3,300 times farther from the sun than Neptune. It is roughly 830 times farther than the heliopause that Voyager crossed in 2012. It is, in light years, somewhere between 0.3 and 1.6 light years from the sun, meaning that the outer edge of the solar system is more than a third of the way to Proxima Centauri. The nearest star and the outer boundary of our own solar system are not separated by the vast, empty interstellar void that most people imagine. They are, by cosmic standards, almost adjacent. The Oort Cloud has never been directly observed. No telescope has resolved individual Oort Cloud objects. Its existence is inferred from the behavior of long-period comets, those comets with orbital periods exceeding 200 years that occasionally fall inward toward the sun from all directions in the sky, unlike the short-period comets of the Kuiper Belt, which tend to approach from the plane of the solar system where the planets orbit. Long-period comets arrive from random directions, suggesting they come from a spherical structure rather than a flattened disk. The mathematical modeling of their orbits traces them back to a source at distances consistent with the Oort Cloud's proposed location. The cloud is real in the sense that something must explain the observed distribution of long-period comets. Its precise structure remains one of the significant unknowns of planetary science. The total number of objects in the Oort Cloud is estimated at somewhere between 1 trillion and several trillion. Not billion, trillion. A vast reservoir of icy bodies, each one a remnant of the solar system's formation, gravitationally bound to the sun, but so loosely bound that the gravitational nudges of passing stars and the tidal force of the galaxy itself can occasionally perturb one of them onto an inward trajectory, sending it on a journey of thousands or millions of years toward the inner solar system where it arrives as a long-period comet visible to observers on Earth. Voyager 1 is currently at approximately 160 astronomical units. The inner edge of the Oort Cloud begins at approximately 2,000 astronomical units. At Voyager's current speed of 17 kilometers per second, it will reach the inner edge of the Oort Cloud in approximately 300 years. It will take another several thousand years to traverse the Oort Cloud and reach its outer edge. Only then, roughly 30,000 years from now, will Voyager 1 have genuinely left the solar system in the most complete and physically meaningful sense of that phrase. 30,000 years from now, using the fastest technology humanity has ever deployed. The scale of this number and what it implies about the relationship between human ambition and cosmic distance is where this story becomes something more than an account of spacecraft capabilities. it becomes a question about the nature of the universe we inhabit and the position we occupy within it. A question that is worth sitting with before moving forward, because the answer shapes everything that follows. If the solar system is this large, if the boundary of our own gravitational neighborhood is 30,000 years away at our best current speed, then what does that imply about the distance to the nearest star? What does it imply about the galaxy? What does it imply about any hope of contact, travel, or connection with whatever else might exist in the universe beyond this small, warm region around this ordinary star? These are not rhetorical questions with reassuring answers. They are genuine physical questions with answers that the mathematics of distance and time makes unambiguous. And the unambiguous answer begins with a single number: the distance to Proxima Centauri in the units that matter most for this conversation. Not in light years, which are abstract, not in kilometers, which are too large to visualize, but in time. In years of travel, at the fastest speed humanity has ever achieved, in the currency of human experience that makes the scale of the problem visceral rather than merely numerical. That number is where this story goes next. And if you are watching this at the end of a long day, if this is the kind of thinking that finds you in the quiet hours when the ordinary world has gone still, then Nocturnal Space is exactly what this channel was built for. Subscribe if you have not already. Every video here starts with a question that sounds answerable and follows it somewhere the answer did not look like it was going to lead. The solar system's true boundary is only the beginning of where tonight's question leads. The distance beyond it is where the real weight of the answer lives. And we are going there now. The Oort Cloud surrounds us. The nearest star is beyond it. And the number of years it would take to get there is one of the most sobering and clarifying facts in all of science. There is a star visible from the southern hemisphere on clear nights, unremarkable to the naked eye, not particularly bright, not the kind of object that draws attention or appears in mythology or gets pointed out by amateur astronomers to impress their friends. It is a small, dim, red dwarf star, roughly 1/8 the mass of the Sun, emitting so little light that it sits far below the threshold of naked-eye visibility from Earth, despite being, by the standards of the galaxy, essentially next door. Its name is Proxima Centauri. It is the closest star to the Sun. And the distance between here and there is the number that breaks every intuitive framework a human being can bring to the problem of interstellar travel. 4.24 light years. That is the distance. 4.24 times the distance that light travels in a full year, moving at 299,792 kilometers per second, without pause or deceleration, covering in a single second a distance that would take a commercial aircraft more than 4 hours to fly. 4.24 years of travel at that speed. The number sounds manageable when stated in those units. 4 years. People take 4-year commitments all the time. University degrees last 4 years. Presidential terms last 4 years. A child born today will be 4 years old before the light currently leaving Proxima Centauri arrives at Earth. 4 years does not sound like an insurmountable obstacle. But 4 light years is not 4 years of travel. It is the distance that light, the fastest thing permitted by physics, covers in 4 years. To travel that distance in 4 years, you would need to move at the speed of light, which is not possible for any object with mass. To travel it in 40 years, you would need to move at 1/10 the speed of light. To travel it in 400 years, you would need to move at 1/100th the speed of light. Voyager 1 is moving at approximately 1/18,000th the speed of light. At that speed, 4.24 light years takes 73,000 years. 73,000 years. This is the number that requires the most time to absorb of any number in this story. Not because it is the largest number that will appear, but because it is the one that lands closest to human experience. 73,000 years is a duration that intersects with human history in ways that make it visceral rather than abstract. Modern humans, Homo sapiens, with essentially our current cognitive capabilities in physical form, have existed for roughly 300,000 years. Agriculture began approximately 10,000 years ago. The oldest known writing dates to roughly 5,000 years ago. The construction of the Egyptian pyramids began about 4,500 years ago. All of recorded human history, every war and empire, and scientific revolution and technological development that has produced the civilization now capable of building spacecraft, fits within the last 5 to 6,000 years. 73,000 years is more than 12 times the entire span of recorded human history. It is roughly 1/4 of the entire existence of the modern human species. It is the time that would need to pass. With Voyager traveling continuously at its current speed without slowing, without deviation, without the mission ending as it inevitably will when its power systems finally fail sometime in the 2030s, for it to reach the nearest star. Not a distant star, the nearest one. The one that is, by galactic standards, our immediate neighbor. Thought experiments exist to make numbers like this tangible in ways that raw figures cannot achieve. Here is one that has been used by astronomers and science communicators for decades because it works better than any other at conveying the true scale of interstellar distance. Reduce the solar system to a scale model where the sun is the size of a grapefruit, roughly 10 centimeters in diameter. At this scale, Earth is a grain of sand orbiting the grapefruit at a distance of about 11 meters. Jupiter is a small marble at 57 meters. Neptune, the outermost planet, is another grain of sand at 330 meters, roughly 3.5 football fields from the grapefruit sun. The entire planetary solar system, from Mercury to Neptune, fits within a circle about 330 meters across. Now find Proxima Centauri at this scale. At the same reduction, 4.24 light-years becomes approximately 3,000 kilometers. Not 3,000 meters, 3,000 kilometers. At a scale where the entire planetary solar system fits in a circle 330 meters across, the nearest star is 3,000 kilometers away. In the United States, that is roughly the distance from New York City to Las Vegas. In Europe, it is approximately the distance from London to Moscow. The grapefruit sun sits on a table in front of you. The nearest other star is in another country, on another continent, visible only as a theoretical point on a map that you could not drive to in a day. This thought experiment does not exaggerate. It does not compress the distances to make the point more dramatic. It is a mathematically accurate scale model. The emptiness between stars is genuinely, structurally, almost incomprehensibly vast. The solar system is an island. The nearest island is not visible from shore. It is not reachable by swimming. It is barely reachable in concept, with technology that does not exist, on timescales that exceed civilization. And Proxima Centauri is the nearest star. The galaxy contains somewhere between 200 billion and 400 billion stars. The average distance between stars in the neighborhood of the Milky Way is roughly 4 to 5 light-years, similar to the distance to Proxima Centauri. The galaxy is approximately 100,000 light-years in diameter. At Voyager's speed, crossing the galaxy would take approximately 2 billion years. The universe is approximately 13.8 billion years old. Crossing the Milky Way at humanity's current maximum spacecraft speed would take roughly 1/7 of the entire age of the universe. These numbers accumulate into a picture that is qualitatively different from simply being large. They suggest something about the structure of the universe that has implications extending well beyond the practical question of interstellar travel. The universe is not merely big. It appears to be structured in a way that makes movement between its constituent parts, at least for physical objects traveling at speeds achievable by any known or theoretically plausible technology, essentially impossible on any timescale relevant to biological life. The stars are not distant in the way that continents are distant, separated by ocean that ships can cross in weeks. They are distant in a way that has no terrestrial analogy, separated by a void so vast that the fastest thing physics permits would need years to cross it, and the fastest thing engineering has achieved would need geological epochs. The question this raises, and it is a question that physicists and engineers and science fiction writers and philosophers have been grappling with for as long as the distances have been understood, is whether this is a permanent condition or a temporary one. Whether the 73,000 years represents a fixed constraint imposed by the laws of physics or an engineering problem that sufficiently advanced technology could reduce to something more manageable. The honest answer requires separating two things that are often conflated: what physics permits in principle and what engineering can achieve in practice. Physics permits travel at any speed up to, but not including the speed of light for objects with mass. It does not permit travel faster than light for any object, massless or otherwise, in a way that transmits information or matter from one location to another. This is not a technological limitation that better engineering will eventually overcome. It is a structural feature of space-time. The same feature discussed in earlier Nocturnal space videos on causality and the speed of light that is as fundamental to the universe's operation as any law of physics ever established. The speed of light is not a barrier that sufficiently advanced civilizations find ways around. It is the speed at which cause connects to effect, the architectural constant of reality, and nothing in physics suggests it has exceptions waiting to be discovered. Within the constraint of sublight speed travel, however, there is enormous room between what Voyager achieves and what physics permits. Voyager moves at approximately 0.006% of the speed of light. Physics permits, in principle, travel at significant fractions of the speed of light, perhaps 10%, perhaps 20%, perhaps in extreme theoretical scenarios approaching 90%, depending on the propulsion technology employed and the engineering challenges that can be overcome. At 10% of the speed of light, Proxima Centauri is 42 years away. At 20%, 21 years. At the speeds proposed by the most ambitious current theoretical frameworks, a few years. These are timescales that begin to approach human relevance, though they remain extraordinary engineering challenges by any measure. The gap between what Voyager achieves and what physics permits in principle is not a gap of 10 or 20%. It is a gap of roughly 4 orders of magnitude, 4 powers of 10. Closing that gap, even partially, requires propulsion technologies fundamentally different from anything that has ever been built. Technologies that draw on energy sources orders of magnitude more powerful than chemical combustion. Technologies that are, in some cases, theoretically well understood but practically decades or centuries from realization. Technologies that, in other cases, remain speculative even at the theoretical level. What those technologies are, how close we are to any of them, and which of them might actually be built in the lifetimes of people alive today, is a story that begins with the elegant simplicity of an ion engine and ends with the staggering ambition of a proposal to accelerate a postage stamp-sized spacecraft to 20% of the speed of light using a laser the size of a city. It is a story about the gap between where humanity is and where physics says it is theoretically possible to go. And it is a story whose most important chapter is not about technology at all, but about what the scale of interstellar distances implies for the question that has been lurking beneath the surface of this entire investigation. If reaching another star is this difficult for humanity, with our current technology and our current understanding of physics, then what does it mean that we have been looking at the galaxy for decades with increasingly sensitive instruments and have found no evidence that anyone has done it? What does the silence of the universe, visible in every direction from every radio telescope ever pointed at the sky, say about whether the stars are inhabited? Whether intelligence is common or rare? Whether the distances that trap us also trap everyone else? Or whether we are simply not looking in the right way? Or whether the silence means something else entirely, something more unsettling than mere distance? That question is coming. But first, the engines. Because before you can appreciate why the distances are so significant for the broader question of life in the universe, you need to understand how close and how far humanity actually is from building something like the journey of a time fighter. In 1998, a spacecraft called Deep Space One fired an engine that produced approximately 92 millinewtons of thrust. 92 millinewtons. For comparison, a single sheet of paper resting on a table exerts roughly 10 times that force on the surface beneath it through gravity alone. The engine was so weak that if you held the spacecraft in your hands and fired it, you would not feel the thrust. You could not detect it without instruments. It was, by the standards of rocket propulsion, essentially nothing. Deep Space One traveled 263 million kilometers on that engine and validated a propulsion technology that has since become the standard for deep space missions requiring efficient, long-duration thrust: the ion drive. And the reason an engine producing less force than the weight of a sheet of paper can propel a spacecraft across hundreds of millions of kilometers lies in a distinction that most people who think about rocket propulsion never fully internalize. The distinction between thrust and efficiency, between how hard you push and how far your fuel takes you. Chemical rockets are powerful and inefficient. They produce enormous thrust, the kind of thrust needed to lift hundreds of tons of spacecraft and fuel off the surface of Earth against the planet's gravitational pull. But they burn through propellant at a rate that makes them essentially useless for achieving very high velocities once in space. The exhaust velocity of the best chemical propellants, the fundamental measure of a rocket engine's efficiency, is approximately 4.4 kilometers per second. Every kilogram of propellant ejected produces a fixed, limited amount of velocity change for the spacecraft, and the rocket equation's exponential relationship means that trying to achieve very high velocities through chemical propulsion requires carrying absurd amounts of fuel. Ion drives work on a completely different principle. Instead of burning propellant in a chemical reaction, they ionize a propellant, typically xenon gas, by stripping electrons from the atoms, and then accelerate the resulting ions through an electric field to extremely high velocities before expelling them as exhaust. The exhaust velocity of an ion drive is typically between 30 and 100 kilometers per second, roughly 10 to 20 times higher than the best chemical rockets. This means that each kilogram of propellant produces 10 to 20 times more velocity change for the spacecraft than chemical combustion would. The fuel goes much, much farther. The trade-off is thrust. Accelerating ions through an electric field requires electrical power, and the amount of thrust producible is limited by the power available to the drive. Current ion drives produce thrust measured in millinewtons to newtons, tiny fractions of what chemical engines produce. This makes them useless for launch from a planetary surface, where you need enormous thrust to overcome gravity quickly. But in space, where there is no gravity to fight and no atmosphere to push through, where you have weeks or months or years for the drive to operate continuously, tiny thrust applied for a very long time accumulates into significant velocity. Deep Space One demonstrated this. Dawn, which orbited both Vesta and Ceres in the asteroid belt, confirmed it. Hayabusa, which collected samples from 2 asteroids and returned them to Earth, relied on it. The best ion drives currently flying achieve exhaust velocities around 80 kilometers per second and continuous operation for years. At that exhaust velocity, and with a reasonable propellant mass fraction, an ion-driven spacecraft could theoretically reach speeds of perhaps 50 to 100 kilometers per second over a long mission, significantly faster than Voyager, but still nowhere near the speeds needed for practical interstellar travel. At 100 kilometers per second, Proxima Centauri is still 12,700 years away. Ion drives are a major improvement over chemical propulsion for efficiency, but they do not change the fundamental character of the interstellar distance problem. They are a refinement within the existing paradigm, not a solution to the underlying challenge. The next step up in ambition is solar sails. The concept is elegant in its simplicity. Light exerts radiation pressure on any surface it strikes. The pressure is tiny, but in the vacuum of space with no friction or drag to overcome, even tiny sustained pressure accumulates into meaningful velocity over time. A spacecraft with a large, lightweight reflective sail could be pushed by sunlight without carrying any propellant at all. The Japan Aerospace Exploration Agency demonstrated the concept with the Icaros spacecraft in 2010, which deployed a 14-meter square sail and confirmed measurable acceleration from solar radiation pressure. The Planetary Society flew its LightSail 2 spacecraft in 2019 and successfully demonstrated controlled solar sailing in Earth orbit. The fundamental limitation of sunlight-driven solar sails is that the pressure of sunlight falls off with the square of the distance from the Sun. By the time you are at the distance of Jupiter, solar pressure has dropped to roughly 4% of its value at Earth's distance. By the time you are in interstellar space, it is effectively zero. A solar sail that starts near the Sun can accelerate rapidly in the inner solar system and then coast on the velocity accumulated there, but it cannot continue accelerating in deep space the way it can near the Sun. The maximum velocity achievable by a solar sail driven purely by sunlight is limited by the intensity of sunlight at the closest safe approach distance to the Sun and the sail's reflectivity and mass per unit area. For current or near-term sail materials, that limit is perhaps a few hundred kilometers per second, much faster than Voyager, but still insufficient for interstellar travel on human timescales. This is where the proposal that attracted more serious scientific attention than almost any other concept in the history of interstellar propulsion enters the story. In April 2016, physicist and entrepreneur Yuri Milner announced Breakthrough Starshot, a research and engineering program funded with $100 million of initial investment, with the stated goal of developing the technology needed to send a small spacecraft to Proxima Centauri within a generation. The scientific advisory board included Stephen Hawking, who appeared at the announcement and called it the moment to launch a new era of exploration. The concept was not chemical propulsion. It was not ion drives. It was not solar sailing powered by sunlight. It was a ground-based laser array of extraordinary power, illuminating an ultra-thin light sail carrying a chip-scale spacecraft, accelerating the entire system to approximately 20% of the speed of light in a matter of minutes. The numbers behind Breakthrough Starshot are simultaneously inspiring and sobering. At 20% of the speed of light, Proxima Centauri is approximately 21 years away. The journey would be fully automated, since no communication with the spacecraft during transit would be practical. On arrival, the chip-scale spacecraft would have seconds to minutes to gather data as it flew through the Proxima Centauri system, at 1/5 the speed of light before continuing outward. The data collected would then be transmitted back to Earth, arriving roughly 4 years after the flyby. The entire scientific return from the mission would be a brief burst of data from a high-speed passage through another star system. But it would be data. Real measurements. Images, perhaps. The first direct information about another stellar system gathered by something we sent there. The engineering challenges between the concept and the reality are formidable, and the Breakthrough Starshot team has been admirably transparent about acknowledging them. The laser array required to accelerate the sail to 20% light speed would need to produce approximately 100 gigawatts of focused power for the duration of the acceleration burn. 100 gigawatts is roughly the total electrical generating capacity of the United States. Focusing that power precisely onto a sail that is accelerating away at increasing speed requires adaptive optics and beam control of a precision that does not currently exist. The sail itself needs to be thin enough, measured in nanometers, and light enough, perhaps a gram for the entire sail and payload, to be accelerated by the laser without being destroyed by it. Materials with these properties at the required scale do not yet exist. The chip-scale spacecraft needs to carry cameras, communication systems, power generation, navigation, and radiation shielding in a package weighing perhaps a gram. The miniaturization required exceeds current technology by orders of magnitude. None of these challenges are violations of known physics. All of them are, in principle, engineering problems rather than fundamental impossibilities. Breakthrough Starshot's position is that the underlying physics is sound, and that the engineering, while extraordinarily difficult, lies within the realm of what sufficiently advanced technology could achieve within decades. Whether that assessment is correct is something that continued research will determine. What is already clear is that the concept has driven serious scientific and engineering investigation into the specific challenges involved, and that this investigation has produced real advances in our understanding of ultra-lightweight materials, high-power laser systems, and miniaturized spacecraft components. Beyond Breakthrough Starshot, proposals exist for propulsion systems that would be more powerful still, capable of moving larger payloads at significant fractions of the speed of light. Nuclear pulse propulsion, originally studied under the classified Project Orion in the late 1950s, involves detonating nuclear explosives behind the spacecraft in rapid succession, with a pusher plate absorbing the impulse of each explosion and transferring it to the spacecraft structure. The specific impulse achievable with fission explosives is roughly a factor of 10,000 higher than chemical rockets. With fusion explosives, which produce more energy per unit mass and cleaner exhaust, the numbers improve further. A spacecraft using nuclear pulse propulsion could theoretically reach 3 to 10% of the speed of light, putting Proxima Centauri within 150 to 500 years of travel time, still longer than a human lifetime, but within the range that a multi-generational mission or a mission carrying suspended crew could potentially manage. Nuclear fusion propulsion without the pulse approach, using a continuous controlled fusion reaction to heat and expel propellant, offers exhaust velocities comparable to or exceeding nuclear pulse, while avoiding the engineering complications of managing discrete explosions. The challenge is that controlled nuclear fusion has been approximately 30 years away from practical realization for the past 60 years of active research. Recent advances in private fusion development have been genuine and significant, with several companies achieving plasma conditions and confinement times that were not possible a decade ago. Whether practical fusion power plants will be operating within this century remains uncertain, but the physical basis for fusion propulsion is well established, and the engineering challenges, while formidable, are not obviously insurmountable. At the theoretical extreme of propulsion, physics lies antimatter. When matter and antimatter meet, they annihilate completely, converting 100% of their combined mass into energy according to Einstein's mass-energy equivalence. No other reaction releases energy more efficiently. An antimatter rocket using the products of proton-antiproton annihilation as exhaust could theoretically achieve exhaust velocities approaching the speed of light, enabling a spacecraft of reasonable mass to accelerate to a significant fraction of light speed with a manageable propellant mass ratio. At 90% of the speed of light, Proxima Centauri is less than 5 years away in the reference frame of a ground-based observer, and due to relativistic time dilation, even less time would pass for the crew on board. The obstacle is production. The world's particle accelerators currently produce antiprotons at a rate that, if every antiproton made in the history of particle physics were collected and stored, would amount to a few nanograms of antimatter. The energy required to produce a gram of antimatter using current accelerator technology would cost roughly $63 trillion at current electricity prices, and the efficiency of the production process is extremely low. Storing antimatter presents its own extraordinary challenges, since any contact between antimatter and the container walls results in annihilation. These are not minor engineering hurdles. They are challenges so fundamental that antimatter propulsion, despite its theoretical elegance, is not a technology that any credible roadmap places within the next century. The honest picture that emerges from surveying these technologies is one of a ladder. Chemical propulsion sits at the bottom, fully mature but fundamentally limited. Ion drives represent the first significant step up, already deployed, already improving, but insufficient for interstellar travel. Solar sails and laser-driven sails represent a more radical departure, with breakthrough starshot pushing the concept to its physical limits for small payloads. Nuclear propulsion sits further up the ladder, theoretically powerful enough to move meaningful payloads at interstellar relevant speeds, but blocked by the decades-long challenge of achieving practical fusion and the political obstacles to deploying fission systems in space. Antimatter sits at the top, physically capable of enabling anything the imagination can construct, but separated from realization by engineering challenges so severe that no serious timeline for its development exists. What this ladder tells us is that humanity is not permanently confined to the solar system by any law of physics. The physics of interstellar travel is understood well enough to identify paths forward that do not require violating any known principle. But the engineering distance between where we are and where we need to be is vast. And the timescales involved in climbing the ladder, even optimistically, suggest that practical interstellar travel, if it comes at all, is a project not for this century, but for future ones. Which raises the question that has been waiting at the edge of this entire story since the very first number, 73,000 years, landed with its full weight. If interstellar travel is this difficult for a civilization that has been developing spaceflight technology for less than a century, and if the galaxy has been around for 10 billion years, containing hundreds of billions of stars with planets circling many of them, then other civilizations, if they exist, have had incomparably more time to climb this ladder than we have. They should be far ahead of us. They should have solved the problems we are struggling with. They should have crossed the distances that confine us. They should, if they exist, and if the distances can be crossed, already be here, or at least visible. And yet the sky is silent. That silence is where the deepest and most unsettling part of this story lives. And it is exactly where Nocturnal Space goes next, because the question of why we hear nothing, see nothing, find nothing, despite searching, despite the mathematics that suggests we should not be alone, is not a question about radio telescopes or signal detection protocols. It is a question about the nature of intelligence in the universe, about whether the distances that confine us confine everyone, about whether the silence of the cosmos is telling us something about the rarity of life, the briefness of civilizations, or something about the structure of the universe that we have not yet understood. If this is the kind of thinking that finds you at the end of a long day, that patient pursuit of the question, underneath the question, subscribe to Nocturnal Space now. Turn on notifications. The next segment is the one where the engineering story and the existential story converge into something that physicists call a paradox, and that everyone else calls one of the most disturbing open questions in science. The universe should be full. The evidence says it is empty. Both cannot be right. And the resolution, whatever it is, changes everything about how you understand the night sky. In the summer of 1950, 4 physicists were walking to lunch at the Los Alamos National Laboratory in New Mexico. The conversation had drifted, as conversations among physicists sometimes do, from the mundane to the cosmic. They had been discussing a recent cartoon in the New Yorker, depicting aliens as the explanation for a wave of flying saucer sightings that had been in the news. The conversation turned, naturally enough, to the question of extraterrestrial life. Were there other civilizations out there? Had any of them developed space travel? Had any of them visited Earth? The discussion was casual, the kind of speculative talk that happens over lunch when brilliant people are not constrained by the formality of the seminar room. Then one of the 4 men, a physicist named Enrico Fermi, who had built the first nuclear reactor, who had made fundamental contributions to quantum mechanics and particle physics, who was by any measure one of the most penetrating scientific minds of the 20th century, asked a question that stopped the conversation. Where is everybody? Not a rhetorical question, not a joke. A genuine scientific question, stated with the directness that characterized Fermi's thinking, that exposed in 3 words a contradiction so stark and so difficult to resolve that it has occupied physicists, astronomers, biologists, philosophers, and anyone else who has thought carefully about it ever since. If the universe is as old and as large as it appears to be, and if the conditions for life are not extraordinarily rare, then other civilizations should exist. And if other civilizations exist and have had more time to develop than we have, some of them should be vastly more advanced. And if some of them are vastly more advanced, at least some of them should have developed the capability to spread through the galaxy, or at least to make themselves detectable across interstellar distances. And yet, nothing. Silence. The sky, examined at every wavelength from radio to gamma, shows no sign of deliberate transmission, no evidence of large-scale engineering, no indication that any intelligence other than our own has ever looked up at the same sky and decided to announce itself. This is the Fermi Paradox. It is not really a paradox in the formal logical sense, a statement that is both true and false simultaneously. It is more precisely a contradiction between 2 sets of seemingly reasonable assumptions. The first set says that life and intelligence should be common in a universe this old and this large. The second set says that if life and intelligence are common, evidence of them should be detectable. The contradiction is that the evidence is not there. Either one of the assumptions is wrong or both are, or we are missing something fundamental about what we should expect to see. To understand why Fermi's question carries the weight it does, you need the numbers. The Milky Way galaxy contains somewhere between 200 billion and 400 billion stars. Observations by the Kepler Space Telescope and subsequent planet hunting missions have established that planets are common, with most stars hosting at least one and many hosting systems of several. The fraction of stars with planets in the habitable zone, the region where liquid water could exist on a rocky surface, is estimated at somewhere between 20 and 50% depending on the definition used and the star type considered. Conservative estimates suggest that the Milky Way contains at least tens of billions of potentially habitable planets. Optimistic estimates suggest hundreds of billions. The galaxy is approximately 10 billion years old in the sense that stars have been forming and planets accreting around them for most of that time. Earth formed 4.5 billion years ago. Life appeared on Earth within the first billion years of its formation. Complex multicellular life took another 3 billion years after that. Technological civilization has existed for perhaps 10,000 years, and spacefaring capability for less than a century. If we assume, conservatively, that Earth is not unusually early in the development of life by galactic standards, then civilizations roughly similar to ours in development have been possible for billions of years. A civilization that developed spacefaring capability just 1 million years before us, a blink in galactic time, would have had 1 million years of additional technological development. If their technology advanced at anything like the rate human technology has advanced in the last century, the gap between their capabilities and ours after 1 million years would be incomprehensibly large. Now apply that to the question of interstellar travel. The engineering challenges discussed in the previous part of this story are real and formidable for a civilization that has been developing technology for a few centuries. But are they still formidable for a civilization 1 million years more advanced? Are they still formidable for a civilization 10 million years more advanced? The entire history of complex life on Earth spans roughly 600 million years. A civilization that emerged from complex life 600 million years ago would have had that entire span to develop its technology while Earth was still in the Cambrian period, populated exclusively by invertebrate marine animals. Whatever that civilization could build after 600 million years of technological development is so far beyond our current capabilities that we have no meaningful framework for imagining it. And yet the galaxy appears empty. No signals, no megastructures visible in astronomical data, no evidence of stellar engineering, no probes detected in our solar system, no radio transmissions in a century of listening. The silence is not for lack of looking. The search for extraterrestrial intelligence program has been operating in various forms since 1960, scanning millions of frequency channels across thousands of stars for any signal that bears the hallmarks of artificial origin. The Breakthrough Listen initiative, funded with $100 million and using some of the world's most sensitive radio telescopes, has conducted the most comprehensive search in history. Nothing has been found that has survived scientific scrutiny as a genuine candidate signal. The solutions proposed to resolve the Fermi Paradox are numerous and cover an enormous range of possibilities, from the mundane to the profound to the deeply unsettling. They can be broadly organized into 3 categories. Either intelligent life is rare, meaning the contradiction is resolved by one of the assumptions being wrong about life's prevalence, or intelligent life exists but is not detectable, meaning the contradiction is resolved by our search methods being inadequate, or our assumptions about what detectable civilizations look like being incorrect. Or intelligent life exists, is in principle detectable, and the silence means something about the nature or fate of intelligent civilizations that we do not want to acknowledge. The rare life hypothesis encompasses everything from the possibility that the origin of life itself is extraordinarily improbable, happening perhaps only once or a handful of times in the entire observable universe, to the possibility that complex multicellular life is rare, to the possibility that intelligence is rare, to the possibility that technological civilization is rare even among intelligent species. The Drake equation, formulated by astronomer Frank Drake in 1961 as a way of organizing the factors that determine the number of detectable civilizations in the galaxy, includes terms for each of these probabilities. Plugging in optimistic values for each term produces a galaxy teeming with civilizations. Plugging in pessimistic values produces a galaxy with perhaps one, which might be us. The not detectable hypothesis includes the possibility that civilizations do not use radio communication in ways that produce detectable leakage into space. A possibility that becomes more plausible when you note that Earth's own radio signature has been declining as communication technology has shifted from broadcast transmission to focused digital signals that are much harder to detect at interstellar distances. It includes the possibility that civilizations deliberately avoid announcing themselves. The dark forest hypothesis popularized by Chinese science fiction writer Liu Cixin, in which the rational strategy for any civilization is silence because announcing your presence to unknown others is dangerous. It includes the possibility that the signatures of advanced civilizations look nothing like what our search programs assume, and that we have been searching for the wrong things in the wrong ways. But the third category is where the connection to this story becomes most direct and most uncomfortable. The Great Filter. a concept introduced by economist Robin Hanson in 1998 that proposes that somewhere in the sequence of steps from the formation of a habitable planet to the emergence of a spacefaring civilization, there is a step so improbable that virtually no chain of events completes it. A filter that blocks the overwhelming majority of potential civilizations from ever reaching the stage where they become detectable across interstellar distances. The question that makes the Great Filter genuinely disturbing is not whether it exists. Given the silence of the sky, it almost certainly does in some form, but where it is in the sequence. If the Great Filter is behind us, if the improbable step is something that Earth has already navigated, then the silence makes sense without predicting our own destruction. Perhaps the origin of life is extraordinarily rare. Perhaps the jump from prokaryotic to eukaryotic cells, which took 2 billion years on Earth and may be deeply improbable, is the filter. Perhaps the emergence of complex multicellular life is the filter. If any of these early steps are the filter, then we are the rare success, the exception that made it through, and the silence of the galaxy reflects the rarity of our own existence, rather than the fate of civilizations like ours. If the Great Filter is ahead of us, if the improbable step is something that technological civilizations typically encounter and fail to survive, then the silence predicts something about our own future that is deeply unwelcome. A civilization-ending technology, an instability inherent to the kind of complex social organization required to sustain a technological civilization, a resource depletion dynamic that all technological civilizations eventually hit, a biological or artificial pandemic, a tendency towards self-destruction that emerges reliably at a certain level of technological capability. If the filter is ahead of us, then the silence of the galaxy is a warning, evidence written in the absence of signals that civilizations like ours typically do not make it. The distance problem explored throughout this story connects to the Great Filter in a specific and important way. One proposed filter is exactly the interstellar distance barrier. The argument goes as follows. Perhaps intelligent life is not rare. Perhaps it emerges on a significant fraction of habitable planets. Perhaps it consistently develops technology. But perhaps the distances between stars are a genuine, permanent barrier that no civilization ever successfully crosses. Not because the physics is impossible, but because the engineering requirements exceed what any civilization can sustain before it either collapses for unrelated reasons or loses interest in a project whose payoff lies thousands of years in the future. If interstellar travel is not merely difficult but effectively impossible given the constraints on civilizations as they actually develop and operate, then the galaxy could be full of civilizations all permanently confined to their home star systems, unable to make contact, unable to colonize, unable to spread, each one invisible to the others across the void. This possibility has a quality different from the more alarming filter hypotheses. It does not predict our destruction. It simply predicts our permanent isolation. A galaxy of islands, each one inhabited, none of them connected, separated by distances that defeat every attempt to bridge them within timescales that matter to any individual civilization, or perhaps any civilization at all. The silence would then be not a warning, but a description of the universe's default condition. Intelligent life exists. Intelligent life is confined. The universe is full and silent simultaneously because the fullness and the silence are both consequences of the same physical fact. The stars are too far apart. Whether this resolution is correct, whether the filter is the distance itself, is something that cannot currently be determined. The SETI programs continue. The theoretical work on interstellar propulsion continues. The search for biosignatures in the atmospheres of exoplanets, which the James Webb Space Telescope is now conducting with unprecedented sensitivity, may reveal within the next decade or two whether life is common or rare on rocky planets in habitable zones. Each of these lines of investigation chips away at the uncertainty from a different direction. What is already clear, and what this story has been building toward since the first mention of 73,000 years, is that the distances separating stars are not merely an engineering challenge. They are a structuring principle of the universe's relationship to intelligence. They determine what civilizations can know about each other, what they can send to each other, what they can become to each other. They are the physical basis for either the universe's loneliness or its silence, and distinguishing between those two conditions is one of the most important open questions in all of science. Voyager 1 is out there, moving at 17 kilometers per second through the interstellar medium. Silent now, or nearly so, its power failing. Carrying its golden record into the dark, it will reach the vicinity of another star in roughly 40,000 years, and almost certainly nothing in that vicinity will find it or know what it is. The universe it travels through may be empty of anyone who would recognize the object, or it may be full of intelligences who would immediately understand every image and sound encoded on the disk it carries, but who are so far away, and the distance is so large that nothing will ever connect them to the species that sent it. Both possibilities are, in their own way, among the most profound facts about the position of humanity in the cosmos. And which one is true, and what we should do in response to either, is where this story ends. There is a gold-plated copper disk aboard Voyager 1. It has been traveling through space for 46 years. It is currently more than 23 billion kilometers from the planet where it was made. It carries, encoded in the grooves of its surface, 115 images of Earth and its inhabitants, greetings in 55 human languages, sounds of wind and rain and surf and thunder, the calls of whales and the songs of birds, 90 minutes of music from cultures across the planet, Bach and Beethoven and Chuck Berry and a Pygmy Girl's initiation song and a Navajo night chant and a Peruvian wedding song, printed instructions for how to build a device to play it, a message from the President of the United States and the Secretary General of the United Nations, a diagram showing where in the galaxy the solar system is located, using pulsar positions as cosmic landmarks that any sufficiently advanced civilization should be able to interpret. The people who designed this disk, Carl Sagan and his collaborators, knew with near certainty that it would never be found. They knew the distances. They knew the timescales. They knew that Voyager would drift through interstellar space for billions of years, threading the enormous emptiness between stars, with an astronomically small probability of ever coming close enough to another stellar system for anything there to detect its presence. They made the disk anyway. They spent weeks selecting the images and sounds. They agonized over what to include and what to leave out. They built it with the kind of care that people bring to something that genuinely matters, knowing that the audience for it, if it ever existed, would encounter it long after everyone involved in its creation had been dead for millions of years. That decision, to send a message into a void where it will almost certainly never arrive, to commit real resources and real human attention to an act of communication that has no practical expectation of response, is one of the most revealing things humanity has ever done. It tells you something about the species that built it, something about what intelligence is for when it confronts the honest scale of the universe and finds that scale neither hospitable nor yielding. Something about the impulse that drives the question at the center of this story, not as a practical engineering problem, but as an expression of something deeper. The honest answer to whether the most advanced spacecraft ever built can leave the solar system is no. Not within any human timescale. Not with any propulsion technology currently in existence. Voyager 1 will still be inside the solar system, inside the Oort Cloud that marks the Sun's gravitational territory, for approximately 30,000 years. At its current speed, it will approach the vicinity of another star in roughly 40,000 years, and it will arrive there without any power, without any functioning instruments, without any ability to collect or transmit data. A dead piece of metal drifting on the trajectory physics gave it in 1977 when Jupiter's gravity swung it outward and released it. The honest answer to whether humanity will ever send anything meaningful to another star is that we do not know. Breakthrough. Starshot proposes a path using laser-driven sails that is physically plausible, but engineering distant, requiring capabilities that do not exist, and timelines that depend on technological development proceeding in ways that cannot be predicted with confidence. Nuclear propulsion offers a more conservative path to speeds that are still insufficient for human interstellar travel, but might enable robotic missions on timescales of centuries rather than millennia. Antimatter propulsion sits at the theoretical limit of what physics permits. enabling anything imaginable if the production and storage problems could be solved, which they currently cannot. The honest answer to whether we are alone in the universe is that we do not know that either. The sky is silent. The searches have found nothing. The mathematics says there should be something to find. The resolution of the contradiction between those two facts is genuinely unknown. And the range of possible resolutions spans from the reassuring, life is common but the distances prevent contact, to the disturbing, something systematically ends. Civilizations before they can make themselves heard, to the humbling, life itself is so rare that we may be the only example in the observable universe. These honest answers are not the answers that make for a satisfying ending to a story about spacecraft and distances and the ambitions of a species that has been pointing telescopes at the sky for 4 centuries. Satisfying endings involve problems solved or paths forward clearly identified. The honest answers are none of those things. They are the answers that remain when the engineering has been examined and the physics has been understood and the numbers have been confronted without flinching. But there is something on the other side of the honest answers that is not consolation, not false reassurance, not a reframing designed to make the limitations feel smaller than they are. It is something more durable than any of those things. It is the observation that the knowing itself is extraordinary. Consider what it means to know these things. To know that Proxima Centauri is 4.24 light-years away. To know this not as a rough estimate or a cultural tradition or a philosophical position, but as a measured fact derived from parallax observations of such precision that the distance is known to within a fraction of a percent. To know the size of the Oort Cloud from the behavior of comets, whose orbits have been traced back through centuries of patient observation. To know the age of the universe from the cosmic microwave background radiation, the afterglow of the Big Bang, imprinted in the temperature of the sky in every direction, with fluctuations measured to better than 1 part in 100,000. To know the rocket equation and its implications. To know the speed of light and why it is a limit and not merely a barrier. To know all of this, with the confidence that comes from independent confirmation by multiple methods across multiple centuries by multiple people who had no interest in reaching the same conclusions and every interest in finding the errors in each other's work. This knowledge is not a consolation prize for not being able to reach the stars. It is one of the most remarkable products of the kind of intelligence that asks questions like the one this story began with. An intelligence that looked at a point of light in the southern sky and determined not just that it was a star, but how far away it was, what it was made of, how old it was, what kind of planets might orbit it, and how long it would take to get there. An intelligence that built a machine, put it on a rocket, aimed it at a planet 400 million miles away, used that planet's gravity to fling it outward, and tracked it for 46 years as it crossed more than 20 billion kilometers of empty space, still receiving its whispered signal after nearly half a century of continuous flight. Voyager 1 is humanity's farthest reach. It is also, in a precise and literal sense, the farthest reach of any known intelligence in the history of the universe. No other species on this planet built it or anything like it. No signal from any other civilization has been detected suggesting that anyone else has done anything comparable. The golden record it carries may be the only artifact of deliberate intelligence currently traveling through interstellar space in the entire observable universe. If it is, then the whisper it is carrying into the dark, the greetings in 55 languages, and the music of Bach and the sounds of wind on a planet 4.5 billion years old, is the universe's only message to itself so far. That is either the loneliest fact imaginable or the most extraordinary one. Possibly both simultaneously. The scale of the universe is not a problem to be solved. It is a fact to be understood. The distances between stars are not an obstacle that better engineering will eventually eliminate. Though better engineering may reduce them from geological epoch timescales to merely civilizational ones, they are a structural feature of the universe's architecture, the same architecture that produced the causal speed limit discussed in earlier nocturnal space videos. The same architecture that makes the night sky dark rather than uniformly bright. The same architecture that sets the boundaries of what any observer anywhere in the universe can know about any other part of it. The universe is not arranged for the convenience of the intelligence it has produced. It is not scaled to human ambitions or human lifespans or human institutional attention spans. It is scaled to something else entirely, to processes that operate over billions of years and distances measured in thousands of light years. And the intelligence that has emerged within it is left to navigate the gap between the scale it operates on and the scale the universe operates on as best it can. What humanity has done with that gap so far is remarkable. In less than a century of spaceflight, starting from the first crude liquid-fueled rockets that could barely clear a field, we have placed instruments in orbit around every planet in the solar system, landed on the Moon, on Mars, on an asteroid, on a comet, sent probes to the outer planets, to the edge of the heliosphere, into interstellar space, built telescopes that can detect the atmospheric composition of planets orbiting other stars, proposed missions that could, within decades or centuries, send the first human-made object to another stellar system at speeds that would cover the distance in a human lifetime rather than geological epochs. None of this was inevitable. None of it was guaranteed. All of it was the result of specific choices made by specific people to direct resources and attention toward the questions that pointed outward rather than inward. The question of how far our best spacecraft can go does not have an encouraging answer in the immediate term. It has an honest answer, and the honest answer is humbling in the way that the best science is always humbling. It reveals that the universe is larger and more indifferent and more structurally resistant to our ambitions than intuition suggests. It reveals that the challenges ahead are not engineering problems that a few decades of clever work will resolve, but civilizational projects requiring sustained effort across generations. It reveals that the silence of the sky may be telling us something about our position in the universe that we are not yet ready to fully absorb. But the honest answer also contains something that the discouraging framing misses. The honest answer is known. The distances have been measured. The physics has been understood. The engineering challenges have been identified with sufficient precision that real work on real solutions is underway. 46 years ago, a piece of human engineering left this planet and is still out there, still moving, still carrying its message into the dark. The species that built it is still here, still asking questions, still pointing instruments at the sky, still working on the next mission and the one after that and the one after that. Voyager will drift for billions of years. The sun will expand into a red giant in roughly 5 billion years, swallowing Earth and ending everything on its surface. Whatever humanity becomes between now and then, whatever it builds and discovers and understands, will play out in the light of a star that Voyager has already left behind. The golden record will outlast the civilization that made it. It will outlast the planet it came from. It will travel through the dark for longer than the current age of the universe, carrying the sounds of a world that will by then have been gone for an incomprehensible span of time. And somewhere in the galaxy, perhaps, something will find it. Or nothing will. Either way, the disk exists. The message was sent. The reach was made, however short it falls against the scale of what surrounds it. And the reaching, the insistence on reaching, even when the mathematics of distance makes the gesture almost absurd, is what this channel exists to think about in the hours when the ordinary world goes quiet and the questions that actually matter have room to surface. Subscribe to Nocturnal Space. Turn on notifications. Leave the word Voyager in the comments if you made it here tonight. Just that word. So we know you followed the whole thing. So we know someone was listening. The disk is still out there, still moving. The universe is still silent. And the question of what that silence means is still open, still worth asking, still worth following all the way down to where the answer lives. We are still reaching,